I thought it would be nice to have a couple of other ways of looking at the definition of derivative. First, I want to look at the epsilon delta way of writing things down. There is such a way of writing things down since derivatives have been defined using limits, and limits are defined using epsilons and deltas. And, sometimes you just have to get your hands dirty and you want to just use some epsilons and work in a really explicit way. And I find it convenient to have the epsilon delta definition around for certain things. So let's just get things set up. Say f maps an open set E to Rm, x is an E, then f prime x we have defined to be a certain linear map from Rn to Rm, if it exists. So it is the unique, if it exists, then it's the unique linear map that satisfies this limit statement. Where here you can see two, let's see, if you put the parentheses like this is the way to interpret it. F prime x is a linear map, and you feed in h, and then you get a vector. And this limit statement has to hold in order to, this limit statement has to hold as the defining property of what is meant by f prime x. Okay, so that's what we have so far. So in terms of epsilons and deltas, what is this saying? It says that, so just translating this limit statement, it's saying for all epsilon greater than 0, and never write like this in your proofs, but I'm just writing schematically here for easy demonstration. For all epsilon greater than 0, there is a delta greater than 0, such that for all h within delta of 0 and not equal to 0. So maybe a simpler way to say that is for all h in Rn such that the norm of h is bigger than 0 and less than delta. We have basically the difference between this and 0 has norm less than epsilon. So in other words, the norm of what's written inside the limit here is less than epsilon. And that's an epsilon delta way of writing things. But we can clean it up a little bit, I think, by moving this. So, that is a large eraser. So let me shrink these norm bars a little bit. This is equivalent to what I had written, and then let me multiply both sides by norm h. And recenter this. Then this is the epsilon delta way of saying things. And when you say it this way, one convenient thing is that you don't have to worry about the case h equals 0. Normally you have to worry about that because you'd be dividing by 0, right? But now that I've multiplied both sides by 0, I can allow h to equal 0 and sort of just acknowledge that that's a trivial case. It doesn't change the definition if I allow h equals 0. Because h equals 0 makes the right-hand side 0 and the left-hand side 0. Well, okay. Slight correction needs to be made. This should be less than or equal to. Okay, but whether you make this a less than or equal to, you wind up with the same overall for all epsilon definition. They're equivalent. So here is an epsilon delta way of saying things. And I like this way of looking at things, partly because it really makes clear what is the role of this linear map here. What we're saying here is that for all epsilon, no matter how small epsilon is, so no matter how small this is, we can choose, by making h small enough, we can make this thing small, which means that f prime x is such that f prime x h approximates this difference. So f prime x h is very close to this. But it's not just the same as saying, you know, that it's not the same as saying that this expression I've circled in blue limits to 0 as h goes to 0. That would also be a way of saying that f prime x h is close to this difference vector. This is something more. It's more than just this, right? It's sort of saying that f prime x of h approximates this difference vector more than just to 0th order, but to 1st order. It approximates it so well that even if you multiply the epsilon here by an h, still making h small enough does make this smaller than epsilon. For any epsilon you pick, there's a way to do that. Okay, that was all maybe a little bit wishy-washy, but let me write down something more precise that captures the same sort of idea. And just remember, if you ever need to get your hands dirty with some epsilons and deltas, this definition is available, and it's pretty convenient. Okay, so let's look at another way of saying things. So now let's define a function. Define a function r by, and let me leave some room to say exactly what kind of function r is, but define r by r of x equals, or r of h rather, equals this numerator here. Remember, x is fixed, right? We fixed x up here. X is the location at which we're thinking about linearly approximating f, or taking a derivative of f. So define r like this. And r is a function of h. So as far as r is concerned, like this is a constant. So just define r like this. And then what we're saying is that 0 equals r of h equals the limit as h goes to 0 of r of h over the norm of h. And just to be clear about things, where is r actually defined? So the domain of f is some set E in Rn, right? And we've got a point x in there somewhere. And we don't actually know where the origin is, but let's just say it's over here. It doesn't need to be a point in E. Then, well, where R, so if you look at R, it involves this f of x plus h, right? So it's not going to be defined for all h's in Rn. It's going to be defined on only some h's in Rn. Specifically, those h's that make it so that x plus h is in the domain of f, in E. So what are the h's such that x plus h is in E? They are those h's that are in sort of a shifted version of E. Let's call this E prime, where E prime equals the set of, let's say, V minus X running over V and E. So this would be the domain of R. Just if you want to say something. So that's the domain of R. And the kinds of things R is outputting is these things, the same kinds of things that F outputs. And R satisfies this property. Okay, so all of this was supposed to be another way of looking at derivatives, and it's not exactly very organized yet, but here is a summary of what we have got. So if we define R like this, then we have f of x plus h equals f of x plus f prime x of h plus r of h. So all I've done is take this and rearrange it, move these to the other side. And this looks like a linear approximation, right? If you want to know the values of f at x plus h, then all you need is the value of f at x and this linear map, which approximates how f varies as you look at inputs near to x. You input into this linear map h, which is the displacement vector between x plus h and x, and you get, you have basically this equation almost holding, with the remainder being r of h. And the limit statement up here, that defines the derivative, now you can think of that as this statement. This is the same thing. It's just saying that the remainder over here gets small as h gets small. And it gets small very fast. So it's not just that r of h limits to 0 as h goes to 0. No, it's more than that. It's that r of h over norm h goes to 0 as h goes to 0. So this goes to 0 fast enough to even defeat this thing going to 0 linearly in the denominator. So hopefully this way of thinking about f prime x makes it very clear that f prime x is a linear approximation to the behavior of f near x. So here's just a picture. Here's the domain of fe, and here's x, where we've taken the derivative and gotten this object, this linear map, f prime x. And it's a linear approximation to the behavior of f near x in the sense that if I take any displacement to the input of f away from x by a displacement vector h over to x plus h, then how does the output change? What's the new output? Well, fx plus h minus fx, or the difference between fx plus h and fx, is going to be given by taking f prime x and applying it to this displacement vector h. So this is our derivative. This is our generalization of the one-dimensional derivative that we interpreted as slope. So this is our new idea of slope. It's a linear map that tells us how outputs to f change to first order when inputs to f are changed. All right, one last comment. about ways of thinking about the derivative, before actually trying to understand what the derivative is doing intuitively, I guess we should really be clear about the type of thing that it is. And I've been somewhat clear, but let's elaborate a little bit. So let's suppose you have f like this, E subset Rn open, then if x is in E and f is differentiable at x, I don't think I defined that officially. That just means the derivative of f at x exists. Then the derivative of f at x ends up being a linear map of this type, right? So f prime x is this kind of object. Okay, well, what if f is differentiable at, say, every x in E? Well then, let's see, let me get my face out of the way here. Then we say f is differentiable on E. This is, again, part of definition 9.11, which I think I never actually stated. But that's what it means to say f is differentiable on a set. It's differentiable at every point of the set. And what is f prime then? What kind of thing is f prime? So f prime needs to be given a point, like x, and then it gives you the derivative at that point, which itself is going to be a map that expects to take a point from Rn and give you a point from Rn. So f prime will have as its domain E, all of the points where f is said to be differentiable. At most, this could be E. F can only be differentiable at a point if that point is in the domain of f, right? And what kind of output is going to be linear maps from Rn to Rn? So if you want to look at, if you have a function that's differentiable at every point of its domain, and you want to look at the derivative of that function as a whole, then this is the kind of thing that it is. It's a function from this subset of Rn, from this E, to this metric space of linear maps. This is going to make it interesting when we think about taking higher derivatives, right? Like back in the one-dimensional world, when we had f prime, we could talk about f prime prime. You know, just if f is a function from the reals to the reals, f prime is a function that goes kind of from the reals to the reals. And so you could take its derivative and then take that thing's derivative and so on and get higher derivatives. But here, just taking one derivative gives you this kind of complicated mapping, right? So it's going to take some thinking to see what should really be meant by higher derivatives. What would it mean to say f prime prime?